Hello everyone, I am Emilie Hummel and I'm here to present a work towards VR training adapted to affective and cognitive states, general method, and evaluation of mental workload. Virtual reality has shown to be useful in various domains and particularly for training users in a controlled environment. With virtual reality, we can explore, interact, and learn in a safe and customizable environment that is particularly helpful in training and rehabilitation contexts. The adaptation of a VR application or task to the user is made possible by the monitoring of their behaviors and enables a personalized experience to better fit the individuality of learners. As a result, adaptive VR leads to better training outcomes. Yet, a literature review on the matter showed that the adaptive logic, meaning the adaptation algorithm that modifies the virtual environment, only takes into consideration the user's performance regarding the training task. But the user's affective and cognitive states play an important role in their behaviors and training results. Affective and cognitive states, or ACS, are composed respectively of the states of emotion and mental and cognitive load. Yet, only one study assesses an adaptive logic based on emotions as an affective state, and no study evaluates the use of cognitive states on the matter. Now, the flow theory aims to quantify the experience of immersion, focus, and engagement under the term flow. A higher flow induces greater motivation, productivity, and enjoyment, which are key elements of training and rehabilitation. Users' flow tends to be higher when the difficulty matches their skills, meaning when the task is neither too difficult nor too easy. Additionally, the cognitive load theory brings a better understanding of cognitive mechanisms during training and learning tasks, and reducing cognitive load in VR training requires to take into account the user-specific features, such as cognitive skills. Adaptive VR training is characterized by the adaptive logic, which, according to Zahabi et al.'s literature review, can fall into three categories: supervised machine learning algorithm, optimization method, and conditional statements. In each case, the input of the adaptive logic is a set of variables that characterize either the users or the virtual elements influenced by the users. We will here focus on online measures that are measured during the task instead of before. The input of adaptive logic is almost always composed of performance measures, which can be motion data, accuracy, task completion, or speed, for example, depending on the context. There's only one study from Abdesalam et al. That adapts the training task to the user's emotions, and one feasibility study from Day et al. That explored the idea of using mental workload. Based on this observation, we propose two contributions. First, an innovative general method to integrate users' ACS for adaptive VR training, and then an implementation of this method to adapt a cognitive task, difficulty to performance, and mental workload. This implementation is assessed through a user study comparing our method to adaptation based on performance only. This method starts from the user interacting with the virtual environment. The user is monitored in real time and their data is fed to a user profile that is composed of the user performance and ACS. This profile also contains the initial state of the user as a baseline, and these states are then used as input of the adaptive logic. The adaptive logic is fed with the real-time measures that are compared to thresholds in order to interpret the data. The initial state, along with the function of the VR application, are used as parameters of the adaptive logic. They set respectively the baseline and the objective for the training and infer the intervention level needed by the user for the adaptation. The adaptive logic then detects the need and priority for adaptation and select the most fitting modification of the virtual environment from a pool of possible adaptations. I will now present the implementation of this method. The VR task we choose is a cognitive task with documents to sort into boxes according to various criteria that are explained on the virtual monitor on the right. The user has limited time to sort each document, as shown by the timer that goes from green to red. And between a set of 5 documents, the user filled a self-assessed mental workload measure on a 10-point scale before starting a new set. The difficulty of each set is adapted from their performance and mental workload during the task. And for the user study, the difficulty levels and starting point were identified in a pilot study. For the user study, we compared 2 conditions of adaptation, the control condition with the difficulty adapted from performance only, and our experimental condition with difficulty adapted from performance and mental workload. The participants performed 20 trials per condition, meaning 20 sets of 5 documents to sort, with the difficulty being adapted between each set. The condition order was randomized. For this experiment, we monitored the online performance, being if participants correctly sorted the documents, and mental workload through self-assessment. We also asked them to complete the NASA Task Load Index questionnaire after each condition and a questionnaire comparing the 2 conditions at the end. Regarding the adaptive logic we used, I recommend you to read the paper as I won't have time to go into details here. Finally, our hypotheses were that we would have a lower mental workload during and after the experimental condition compared to the control condition. No difference for performance between the 2 conditions, and that our experimental condition would be experienced as more successful, less stressful, and preferred by the participants. Now we'll briefly show you some results. So among our 30 participants, most of them were novice or occasional VR users. The NASA Task Load Index scores show a significantly lower mental workload for the experimental condition. You can see here the detailed sub-items with significantly higher mental demand, temporal demand, effort, and frustration, and lower performance for the control condition in red compared to our experimental condition in blue. Regarding the online measures, despite a good performance in both conditions, we measured a significantly higher performance and lower mental workload for our experimental condition in blue. Finally, you can see here which condition was found most successful, more stressful, and preferred. The participant had to choose one of the 2 conditions represented by the dots and give their confidence level from 1 to 5 regarding their answer. The shape of the dots indicate which condition they did first. As you can see, most participants found the control condition less successful, more stressful, and less preferred compared to the experimental condition. Our results support H1 and H3, but while we expected to find no difference in performance, the participants performed better in the experimental conditions compared to the control condition, which does not support H2. This can be explained by the slower progression of the difficulty in the experimental condition to limit the increase of mental workload. With a within-subject design, our results were affected by the condition order effect. While they are still promising, their generalization cannot be ensured yet without additional work. Regarding the difficulty progression, the participants tend to reach a plateau after a while, but we observed another increase of the difficulty after the plateau during the experimental condition only, suggesting that this method better fits their natural progression. It would be interesting to focus on this aspect in a future study. Finally, we did not measure any impact on the repeated self-assessment on flow, showing the feasibility of repeated subjective measures for adaptive VR. So to summarize, we introduce here 2 contributions, a general method integrating ACS for adaptive VR, and a user study assessing an implementation of this method. We showed the feasibility of such approach for real-time adaptation and the viability of repeated measure, both objective and subjective, to monitor the user's behavior. Our adaptation logic based on performance and mental workload shows significantly better outcomes than state-of-the-art adaptation, and our user study highlighted important leads for future research, such as better understanding the order effect and the change of difficulty progression that can happen during the user's progress. Thank you for your attention. If you have any question regarding this work, you can contact me by email or through the QR code here.